good morning. This is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. I am going to present the lecture 6 on the topic of the stress formation and the analysis of the stresses on the topic of the strength of material subject, which was developed in the National Program of Technological Enhanced Learning. If you see that, like the previous lectures, we discussed about that what are the like the resultant stresses are there at the oblique plane if there is a if the material is subjected by the pure normal stress, or what will be the stress components are there at the theta as well as the normal stress component or the shear stress component if the material is subjected by pure shear, or if we have two combined stresses, means two mutually perpendicular stresses like the normal stress component sigma x and sigma y, if the material is subjected by that, then what will be the stress component at the oblique plane? Sigma theta means the normal stress component and the shear stress component. So these like the components, the sigma theta and the tau theta means the this normal stress component as well as this shear stress component, we have already like discussed and calculated that actually what the impacts are there, and also we just put the different conditions to get the value of the maximum as well as the minimum shear stresses if you see if a component is subjected by both. So the last like the discussion was there, which was pretty fruitful, that if a material is subjected by both, if we have the mutually perpendicular stresses as well as the shear stress component is there. So if there is a combination of these like stress components like sigma theta, the sigma x, sigma y and tau xy, then what will be the resultant like the stress components are there like the normal stress component and the shear stress component at the oblique plane, because if we cut the plane at an theta, that is the oblique plane, and we just want to formulate those things. So that's what you see, we discussed that if these three components are applied at the same time, means the sigma x, sigma y and tau xy at the plane, then we had the sigma theta, which is equals to sigma x plus sigma y by 2, which is independent of the theta, plus sigma x minus sigma y by 2 into cos of 2 theta plus tau xy sin of 2 theta. So this was the first, you see, the normal stress component at the oblique plane if these three stress components are there. And also we formulate that actually if the other component was there, the shear stress component tau x the tau theta, which is pretty like the combinational effect is there by sigma x plus sigma x minus sigma y by 2 into sin 2 theta plus tau xy this cos of 2 theta. So that means you see like if we see either the sigma theta or tau theta, we found that there is the combined effect is there of sigma x, sigma y and tau xy. And also we calculated that actually if you want to find out that in the component where the maximum or minimum values of these normal stress components are there, then we observe that there are some of the places where these maximum or minimum normal stress component is there, and those planes are known as the principal planes, and whatever the stresses values are there, like you see sigma 1 and sigma 2, these stresses are known as the principal stresses. So you see we calculate that sigma 1 is nothing but equal to sigma x plus sigma y by 2 plus square root of sigma x minus sigma x minus sigma y whole square plus 4 times of tau square xy. So this was the first principal stress, and second principal stress was sigma x plus sigma y by 2 minus square root of, that was the, you see the hypotenuse was there, sigma x minus sigma y whole square plus 4 times of tau square xy. So these were the two stresses which we found that these are the principal stresses, and these are always occurs at the principal planes, and we can find the principal planes by differentiating the sigma theta with the theta in keeping 0, and you see we found that there is a location, and that location we can calculate by 2 times of theta p, which is equals to tan inverse of 2 times of tau xy divided by sigma x minus sigma y. So you see these kind of discussion which we made, and also we found that, which is a very important observation was there, that the principal planes are always occurs where there is no shear stress, means you see wherever the shear stress is 0, we had like the principal stresses which are sigma 1 and sigma 2. Also we discussed that actually we can get the maximum shear stresses, like you see the location was tan of 2 theta s, which is equals to the sigma x minus sigma y divided by 2 times of tau xy. So you see we had a relation, the last part which we discussed in the previous lecture was we had a relation with the theta p as well as the theta s, that means where the maximum shear stress is there, where the maximum normal stress component is there. So the relation was tan of 2 times theta p into tan of 2 times theta s equals to 1. That means you see they had a reciprocal relations to each other. So this kind of relations which we made in the previous lecture, and then also we discussed that we had we can solve by two methods. One is the analytical solution, that means the numerical solution is there, that what the angles are there, you see, and by putting all the trigonometric relations we can observe that okay, now these are the places if a component is there which is subjected by many of the forces, we can easily resolve those forces if we know, and if we can also find it out that actually where these stress values means the internal intensity of the resistances are the maximum, or what is the stress concentration is there in this particular component, just by knowing those trigonometric relations about this particular object. So this is the one method, but the popular method is the graphical solution. So in this particular lecture we are going to discuss in detail that what is the graphical solution is there, and generally you see it termed as that it is a Mohr circle, means you see with the inducing effect of the two mutually perpendicular stresses, the normal stresses sigma x and sigma y, with the third stress, that is the parallel stress. You see if we have a component and there the parallel stresses are there, these are tau xy, and at the same time you see to balance the this component under the effect of this shear stress, we had a counterbalance shear stress, that is known as the complementary shear stress tau dash. So you see here under all those stress components, if our material is well balanced, we can say that yes, all the stresses are well set within those objects, or we can say under the influence of these forces, the external forces, we are in the equilibrium position, and that's what you see all those principal stresses, principal planes, or the location of the principal stresses like that, or the location of the maximum shear stresses within those objects are valid if our this material, or we can say the object is equilibrium under influence of these stresses. So now you see the lecture 6 here. As I told you, now in this lecture we are going to start with the graphical solution, that is the Mohr stress circle, because you see we are only dealing with the stresses right now. So here the transformation equations, like you see the sigma theta, tau theta, all those things for the plane stress. The plane stress means you see the two-dimensional stress in which you see these the plane is there, either the xy, yz or zx can be represented in a graphical form known as the Mohr, because the Mohr is a well-known French scientist was there who generated this kind of this graphical solution. So based on that, actually we simply named this particular graphical solution as the Mohr circle. This graphical representation is very useful in depending upon the relationship between the normal as well as the shear stress. As I told you, see now in this particular case which we discussed, the last thing was we had two mutually perpendicular normal stresses are there, and there is only one shear stress component. That means you see we have three mutually perpendicular stresses, one is parallel to axis, one is two mutually perpendicular axis. So all three, you see the two normal stress component and one shear stress component, if they are acting, then how you see we can formalize the stress component, and then what will be the resultant the stress component is there at the inclined plane, that is the oblique plane, you can say, at a point in the stressed body. So this, you see, this kind of the transformation as well as the relation we just want to describe on a graphical solution. So now come to the main point. You see that to draw a Mohr stress circle, consider a complex stress system. As we discussed, you see that if we have first if you see this figure, then we have this sigma x on both of the side. So you see this stress component is the normal stress component in the x direction. We have the y direction, means the normal stress component in the y direction, that is the sigma y, which is you see perpendicular to the y section, and we have the same time the shear stress which is parallel. You see the AB as well as the CD, we have the shear stress component tau xy which is parallel to the plane. So to counterbalance those, you see the shear stresses, what we have the tau xy, this is the counterbalance, so it is known as the complementary shear stress. So we have both the component at AD as well as the CB. So you see this material, whatever the material which we have, it is subjected by three stresses, the two stresses are the normal stress component sigma x, which is in this direction, as we can see in this figure, sigma y which is in this vertical direction, and the tau xy which is in this figure. Then we would like to see the resultant of the combination of these stresses. So that's what we did here. We simply cut the plane at theta. So you see this PC is the cutting part, which is, you see, we simply cut at the theta angle. So this is our angle of measurement. So we just want to measure those things, and then you see at this particular plane we have this PC plane. So normal to this plane we have a normal stress component, that is the sigma theta, and we have a parallel stress component, that is the tau theta. Means this normal stress as well as the shear stress components are there, and you see we have already stabilized the relation this analytically. So now you see here the system represent a complex stress system for any the condition of the applied load in these two dimensions, like you see the x and y. The Mohr circle stress, whatever you see these, is used to find out the graphically the direct stress sigma as well as the this shear stress tau at on this particular plane, the theta plane, which is inclined at tau to the plane on which the sigma x is acting. Okay, and the direction of tau here is taken as the anti-clockwise direction from the BC. So you see here whatever the tau is there, it is just because it just tries to oppose that thing. So we have the shear stress which is exactly opposing to the concerned shear stresses. So now in order to achieve whatever the the desired objective is there, because we just want to calculate what the resultant tau is there, we just want to represent also at the same time what is the resultant tau, means the shear stress, what is the resultant sigma, that is the normal stress component. So you see there is a step for that. So first of all, you see, once you know that you have a material which is a kind of a regular shape, you simply noted, you just simply noted or simply labeled those corner points. So here you see we have a simple the square part is there, so just label that block A, B, C, D. So now you see we have A, B, C, D. So the AB at AB plane or this particular like the CD plane, we have the shear stress component, that is the tau xy, and at these two corners either the you can say the CD or AB, what we have just these planes normal to those planes, we have the normal stress component, that is sigma x in x direction, sigma y in y direction. So first label those A, B, C, D. This is the first step. The second step is the set up the axes for the direct stress. That means you see whatever the direct stresses are there, now set those axes as a abscissa. Means you see because if you want to make the circle, you see we need to have the two, because it's a plane stress, so both the stresses are there. So just for abscissa you need to put the direct normal stresses, that means the sigma. And you see on the this ordinate side, means the vertical side, what you need to put? You need to put the shear stresses. That means you see now whatever the stresses are there in the this complex stresses are there in the real manner, now you see we are transferring those stresses in the Mohr circle by keeping x-axis with the direct stress component, that means the sigma only, and vertical direction it is the shear stress only, tau. Okay. Now you see plot these stresses on these two adjacent faces, that means you see either AB or BC using the following sign convention. So you see here, if we want to plot whatever the resultant stresses are there, first of all we have to be very careful that actually what exactly the stress, the direction of the stresses are there, because you see whatever the direction is there, we have to be very careful that actually what exactly the sign is, whether it is the summation of there, means the resultant part, the summation of there, or they are cancelling to each other, or what exactly the interaction is there in between these stress components. So you see first of all, if we are looking at the sign convention of these stress components, then first of all we found that there is a direct stress component, and the direct stress component you see we have, if there is a pulling in the normal stress, that means you see if there is an extension is there, we are always taking the positive, and that is known as the tensile stresses or tensile loading you can say. And if there is a compression, or which you see the internal intensity of the this forces, they are always just try to go towards outward direction, always there is a compression is there inside the object or the outside external surrounding, always take the negative direction. So you see as well as the normal stress components are there, which is pretty standard thing is there, tensile is always taking positive, compressive always taking negative sign. And if you are looking at the shear stress component, as we discussed that actually, because they are always across the layers of the object, we always see that what is the tendency of this shear stress component, because if you see if it just tending to turn the block, whatever the ABCD block is there, in the clockwise direction, means you see like this thing, they are acting in this direction and object is moving towards this direction, always take the positive side. And then you see we have the complementary shear stress component, which will just try to resist this clockwise motion. So if you see we have this kind of the shear stress component, which will just try to means actually this one, if these shear stress directions are there, and if they are tending this particular block to move in the anti-clockwise direction, always take the negative direction. That means you see shearing stresses are positive when the movement or the tendency of the block is towards the clockwise direction, or the element is just tending to move towards the clockwise direction, or if it is moving in counterclockwise direction, that means you see it is the negative direction. So these are the sign convention, and we are very much like strictly we need to follow those, that if the tensile in the normal stress component, the tensile is there, always take positive, compressive is there, always take negative, shear stress if it is moving towards clockwise take positive, if it is moving anti-clockwise take negative. So just keep this thing in your mind, and by keeping those things, that you see we have like the abscissa with the normal stress component, like the ordinate, the y-axis with the shear stress component, and these sign conventions, now we can easily find it out that what is the Mohr circle is. So you see the next slide is going to present you that what exactly you see those combinations are there, and with inclusion of those combination, how we can draw the this Mohr circle diagram. So you see now here this gives the 2 points on a graph which may you see labeled as represented by like the stresses on these particular planes. First of all, you see you have sigma x and sigma y on x axis, so you need to label, you need to join those things, that what is the value of the sigma x is there, what is the value of the sigma y is there, and what is the combination is there. So you see, because we have the two normal stress component, so just join those two component on these particular planes. So we have one plane that is a sigma plane, and if we have the tau plane, again we have to be very careful that actually whether this tau xy is positive, means about 0 in the first quadrant, or it is negative, means it is in the fourth quadrant, like that in the below side. So the point P, you see, which is the cutting plane is there. So wherever the cutting plane was there at the theta, like this point P where this line cuts the sigma axis is now like the center of the Mohr circle, and line joining is the diameter. So you see here now the two main features have come in this particular line. First, whatever the cutting part is there, the extreme end point on the top of the surface gives you the center of the Mohr circle. Whatever the location of the point P is there, this gives you the circle, the center point of the Mohr circle, and the line joining of the whatever the diameter, means you see if it is just passing through from these things, it will give you the diameter. So therefore you see the circle can now be easily drawn with the using of all the information which we discussed here. So now you see here this is the Mohr circle. Now every point on the circle now then represent a state of stress on some like the plane through center, or we can say the C. So now we can look this particular circle. You found that as we discussed, this is you see like the x axis where the normal stress component is there, this is y axis where the shear stress component is there. So now by taking all the information of that we have, you see a material which is subjected by two normal stress component and the shear stress, you see the shear stress is passing under the combination of all three components of the stress. Now we see how we can formulate. So now what we have, sigma theta and tau theta. What is the sigma theta? Sigma theta is sigma x plus sigma y by 2. So sigma x, you see now you can straightway plot that this is my sigma x. So sigma x is nothing but this BC is there. So if you plot these things, now this is my sigma x, okay, and whatever you see this diameter which is passing from these things, we have if you drop this line, the project this line on the x axis, because whatever the sigma x and sigma is there, sigma y is there, it is nothing but the interception of these points, this BC bar or AB bar on a x axis. So if you see we have the point P which is the center point, take the radius and draw the circle. So wherever you see you found that by simply clicking of this particular, you see now this we have the x axis and we have the beta angle. So once you rotate this beta angle, you found that from P to BC bar we have the radius. Radius is nothing but equals to square root of sigma x minus sigma y by 2, sigma x minus sigma y whole square plus 4 times of 4 times of tau square xy. So once you calculate these things, this P into P to BC bar, that is the radius, simply intercept this the project this particular part on the x axis, you will get the sigma x. Similarly, you see once it is passed through the P, and it will give you see this is the whole diameter of that. So we have the AB dash, simply intercept this part, the tau xy, and on the x axis whatever the distance is there from O to this part, this will give you the sigma y. So this is sigma y. So now you see we have sigma x, we have sigma y, so you can calculate the total sigma theta, which is nothing but equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos of 2 theta. So now you see, if you want to calculate the cos of 2 theta, now you look at this point, that what is the 2 theta. So 2 theta is nothing but equals to, right from this first the projection. So this was the first projection from P to BC bar. So from here you see, you can simply plot the 2 theta. So now you see here, this one is projected. That means you see, now this is simply projected by that. Earlier this was there, now you see the 2 theta is this, and if you simply rotate by beta degree, that means you see the beta one, this one. So we have, you see, 180 minus beta of this part, or else you can say this, from this part you can get the exact value of 2 theta minus beta, means actually what exactly the difference is there in between the projected angle and the measured angle. So this is there. So the meaning is that whatever the information which we are carrying in the numerical way, that means you see, irrespective of the sigma theta or tau theta, you can simply plot irrespective of whatever the relation is there from the Mohr circle. So you don't have to calculate if the complex stresses are there and the complex formation is there under the material concern. So here again, starting from that, this is sigma tau, simply plot those, like simply get the value of the radius. Once you have the radius, plot the diameter. Once you have the diameter, make the projection. So once you make the projection of the theoretical axis on the horizontal axis, then you have both the components sigma x and sigma y. This is pretty easy. Or you can say in vice versa, you have sigma x, you have sigma y, you have tau xy. So it's pretty easy for you, because once you know the sigma x, straightway take from the origin, draw the sigma x and make the vertical projection wherever it meets to this like one point. Just you see, like make those points, and this is, you see, the one point. Take another point sigma y, so straightway you see on the y on the x axis, this is my sigma y, and then take you tau xy, so this is the tau xy. So once you have, you see, this point from the sigma x and tau xy, you have from the another point from sigma y and tau xy. So now make the this diameter, and once you have the whole diameter, take the point of the center, you see, on the x axis and draw the circle. And once you draw the circle, you have all the information required. Means you see, you can easily draw, irrespective whatever the information which you have, you can simply plot the Mohr circle. So you see, now this is the well generated form of the Mohr circle. Means what we did here, we simply convert whatever the information which we have. Means you see, we have like the sigma x, sigma y and tau xy. So based on these three information, in the previous figure we have shown that, you see, like how to plot all those, you see, the curves, means the diameter and the Mohr circle. Now you see, we converted that actually wherever, you see, where the minimum and the maximum value of the normal stress component is, and those values are known as the principal stresses. So you see, now this is the conversion of the simplest form of the stresses, because you see, if we have both this mutually perpendicular stresses sigma x and sigma y, and if we have the tau xy, this is sort of the complex form of the stresses, because you see, if you want to calculate the resultant of these stresses, then you found that it is very complex. So what we need to do here, we just want to make this general state of stress. So that's what you see, like in the previous lecture also, we converted all those combined this complex stresses into the normal stress, into the simplest stress, and those stresses are known as the principal stresses. So here you see, like starting from that sigma 1 is nothing but, because we know sigma x, sigma y and tau xy, sigma 1 easily calculated, like we have sigma 1 is nothing but sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by sigma x minus sigma y whole square plus 4 times of tau square xy. So you see, now you have the sigma 1, which is, you see, the maximum value, the summation is there, sigma 2, which is sigma x plus sigma y by 2 minus square root of sigma x minus sigma y whole square plus 4 times of tau square xy. So you see, here you have both the maximum value of normal stress, because the normal stress component is there on this plane. So this plane is the principal stress 1. So you see, this is principal plane, or which you see the principal stresses are there. So we can simply note both maximum value of the principal stress, that is the sigma 1. So you see, once you know this the maximum value, simply take on the x axis, and if you know the sigma 2, that is the minimum value of the principal stress, then put the sigma 2. So now you see, you have sigma 1, sigma 2. So wherever, like it interacts, you have the full diameter of these things. So you see here, if you can simply calculate the coordinates of P, that is nothing but the sigma 1 plus sigma y by 2. So that is, you see, like this one. So you see, you can straightway first locate that what is the coordinate points are there of the center point of the Mohr circle. That is nothing but, if we are talking about this principal stresses, then it is sigma 1 plus sigma y by 2. Once you plot these things, now you see what we need to do here. We are simply, first of all, you need to rotate these things by 2 theta, because we know that tan 2 theta p is nothing but equals to sigma x minus sigma y divided by 2 tau xy. So you see here the 2 theta p can be easily like rotated. So you need to rotate these things. So now it is rotated. So we have the BC bar, or we can say this BC bar is nothing but equals to either you can take this is sigma x and tau xy is there. So you see here pretty simple, the sigma x which is nothing but this distance, and you see the tau xy of this distance. Similarly, you can plot also the AB bar, which is nothing but equals to this is the sigma y. So once you have the sigma y, and you can also put the tau xy. So you can plot this thing either one way, or another way is you have this particular just simply rotate this main axis where you see the sigma 2 and sigma 1 is there. Rotate this part by beta, or you can see the 2 theta p where you see the principal planes are locating, and then you see you can get those on this particular the circumference of this Mohr circle. You can get both the values of both the points of the principal planes. So you see here, one we have AB bar, once we have the BC bar, you have sigma 1, sigma 2, you have sigma x, you have sigma y, and you have tau xy. So what exactly the relation is there, it's pretty easy to find it out. And another, you see, if you are saying that now it is rotating where the maximum shear stresses are there, so again you can rotate by 2 theta s, and you can get the value of the P to Q. So you see here, now if you rotate these things by 2 theta, now you have these things, you see. So pretty simple, you can simply make the circular part here, this either one, and the another is this one circle. So you see both the like the triangle are pretty straight. Only you simply making the relation between the sigma x, sigma y, and tau xy. If the combination is there, all the simplest form is sigma 1 and sigma 2 if the principal stresses are there or the principal planes are there. So this is all about the Mohr circle. In the previous diagram it was with the complex form is there, and in this form it was a simple principal stress formation. So you see here, consider any point Q which one you see angled by 2 theta on the circumference of the circle, outer periphery of the circle. We just found that like the PQ makes an angle of 2 theta as we discussed. You see with the BC, whatever the BC on this particular plane is there, drop a perpendicular from Q as we drop that with the sigma x, that means the x axis, and it is meeting at the end point. Then you see we have the OQ. you see O is the origin of the point, Q is that point where you see we are meeting. So OQ represents the resultant stress on a plane at an angle of theta, so to the BC. So you see here as pretty simple, we are assuming that the sigma x, whatever the x component is there, because it is in our abscissa, you see that means you see our x axis, so always it is sigma x is greater than to the sigma y. That means you see this is a simplest assumption is there. With that assumptions we can simply say that sigma x and minus sigma y will be positive, and accordingly you see the direction of the rotation is there of the shear stresses. That's why we are assuming this sigma x is greater than to the sigma y. Now you see, let us find out the coordinate of the Q, because you see it is rotated by 2 theta from the main angle. So you see what exactly means main angle means AB to BC bar. We simply rotated in the previous figure. If you see previous figure, so that's what you see if we rotated, then what the new coordinates of the this Q is. So what we did here, simply we have chosen the two things, one is the ON and one is the QN. So here from the figure, you see from this figure we found that this figure, this is the Q point. Okay, so what we did here, simply we want to calculate that actually if we drop those things, then what is the Q to N part is there, means what the the coordinates are there, and what the coordinates of the Pn. So now what we have a triangle PQN, and we just want to find it out, because you see all other coordinates like this tau xy, sigma x, r, tau y, tau xy, all those coordinates are well established, pretty well known things. But as far as this thing is concerned, which is because it is simply rotated by 2 theta, then what is the new formation of the Q is, we want to find out the coordinates, and we want also to want to set up the relation between the P to N, P to Q, and Q to N. So that's what you see. You see here from that figure. Now we simply say that the ON is nothing but equals to OP plus PN, or we can say that this OP which is coming the horizontally, OP is nothing but there is a middle point, that is OK to KP. We can simply confirm these things. You see, this is O to P. O to P is nothing but equals to O to K into O to K plus K to P. So this is, you see, like this OP can be easily divided, and like this was there, OP was nothing but the OK plus KP. So we have discussed in the previous slide that actually there is a straight relation with the OP to ON. So we would like to see that actually from the Mohr circle, how we can get the like the value of the OP. So you see here in the OP is nothing but equals to the sigma y plus sigma x minus sigma y by 2. Again, you see here the biggest assumptions which we made here is sigma x is greater than sigma y. So that's what you see, like sigma x, if you deduct sigma x minus sigma y, it gives you a positive value. So here, by taking the consideration of these assumption, we have OP is, you see, right from origin to the center point, you see we have what sigma y, which is, you see, the O2 K, and K to P was sigma x minus sigma y by 2. Okay, so you see, if you compare those things, then what we have, sigma y by 2 plus sigma y by 2, simply like divided into these two form, plus we have sigma x by 2 plus sigma y by 2. So the all in all, you see, if you like relate those things, then what we have the sigma x plus sigma y by 2. That means, you see, OP also, you see, if you are going for this principal stresses, then we can simply locate the P position by sigma 1 plus sigma y by 2 if the principal stresses are there. But if we are talking about like that if we have the normal stress component like sigma x, sigma y and tau xy, we can also find it out that the P location is nothing but equals to sigma x plus sigma y 2, which is proved here. And then you see the P to N. P to N is nothing but, you see, the N is the point where the projection was there from the Q. So P to N is nothing but R of cos R into what is the result, R means the radius into cos of 2 theta minus B. So 2 theta minus B was the angle, if you just remember that figure. So 2 theta minus was the B, and the R was the like the radius. So if you make the positive like the resolution of this force, then you find that Pn is nothing but equals to R into cos of 2 theta minus B. So you see here, it's pretty simple. On is nothing but equals to, again go back to that, OP plus Pn. OP is nothing but equals to sigma x plus sigma y by 2. So this is sigma x plus sigma y by 2, and Pn, which is the like the cos resolution of this R, so R times of cos of 2 theta minus B. Or we can also use this, you see, if we expand this, cos A minus B is nothing but equals to cos A cos B plus sin A sin B. So by resolving these things, we have sigma x plus sigma y by 2 plus R times of cos of 2 theta cos of beta by this plus R times of sin 2 theta sin beta. So what we have now O to N. O to N is nothing but equal to, see, the O is the origin, the starting point on the x-axis, N is the point where you see the Q is dropping. So we have the total dimension of ON by summing of the OP to PN. So now you see, now making the substitution of R cos beta and R sin beta, you see, we can simply like get the value. R cos beta is nothing but equals to, you see here, these are the substitution which we need to make, and we can get these things by the geometry itself. So what we have R cos beta is nothing but equals to sigma x minus sigma y by 2, and R sin beta, which is nothing but the tau xy. Again, this is a very like good assumption. If you go back to like those figure, which is a Mohr circle, you'll find that the beta is that angle, and the first circle, I should say, in the first circle you can find that the beta is the angle, and in the beta you can easily calculate, you see, because it is just sloping with the R. So R of the positive slope, R cos beta, will give you sigma x and sigma y by 2. In between that, sigma x is this, sigma y is this, so sigma x minus sigma y by 2, and the tau xy, the vertical component, will give you the sine of beta. So sine of beta is nothing but the tau xy divided by R. So you see, from that you can easily get this value cos beta and sin beta. So you see, if we are keeping these values here, we have O to N, is origin to the last point, O to N is nothing but equals to sigma x plus sigma y by 2 plus half of sigma x minus sigma y by 2. And now you see, like we can simply keep these things. So cos of 2 theta plus, you see, the tau xy, which is R sin theta, was there. So and this sigma x minus sigma y by 2 was the R cos theta. So sigma x minus sigma y by 2 cos of 2 theta plus tau xy sin of 2 theta. Similarly, you see, like we can also calculate Q to M. So you see here, because this is the end part was there in that particular way, so you see, you can also calculate the Q to M, and Q to M is nothing but equals to the another the resolution of the force. The first formation of the force was there, that r cos of 2 theta minus b. Now you see, if you go back to the 90 degree, then you have q2m, that is r sine 2 theta minus b. Or you see, we have, you see, if we can simply keep the formula of sine a minus b is nothing but equal to sine a cos b minus cos a sine b. So by keeping that formula here, we have q2m is nothing but equals to r times sine of 2 theta into cos beta minus r times the sine of cos 2 theta into sine beta. So you see here what we have in the previously, if you see, then we have the on we always get by Pn, which is r cos theta b, and you see this is the Pn, and then we have the q2m, which is r sin 2 theta b. So if you resolve those things, we have both on as well as the qm. So now you see, by keeping those values, r cos theta r cos beta, which is nothing but equal to sigma x minus sigma y by 2, or r sin beta, which was the tau xy, by keeping those values in the previous formula, like this qm. So now you see what we have, the qm is the new formulation of the qm is sigma x minus sigma y by 2, which was the value of r cos beta into sin theta minus tau xy, which is coming because of the r sin beta into cos of 2 theta. So if you see both the formation irrespective of the qm or pn or on, so on is nothing but equals to, we have sigma x plus sigma y by 2 plus this sigma x minus sigma y by 2 cos of 2 theta plus tau xy sin 2 theta, or we have this qm. So you see here, these two equations are pretty close to calculate those things. But if we examine the equations 1 and 2, the previously, see, we found that these equations, the physical signs of these equations are pretty same, which we we have already derived analytically from the previous equations. Means that you see what we have, if we want to calculate the theta, the sigma theta, what was the value of the sigma theta? Sigma theta was nothing but equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos of 2 theta plus tau xy cos sine of 2 theta. So same equation, sigma theta means on means it is the normal stress component at the inclined plane. Here you see we are considering the inclined plane is at beta. So you see here we have on is nothing but the sigma theta. So this is the sigma theta formula, which is exactly similar to on. And then you see the tau theta was the shear stress component at the oblique plane where the theta angle is there. So similarly, if you compare these things, then you find that the tau theta was sigma x minus sigma y by 2 sine of 2 theta plus tau xy cos theta. So here you see only the difference is what the rotation is there. So here the qm is the tau theta, that means the shear stress at the theta angle, which is again the similar thing is there, tau xy minus tau x minus tau y by divided by 2 into sine of 2 theta minus tau xy cos of 2 theta. That means you see you have, if you want to calculate either this on, which is the sigma theta, or qm, which is the tau theta, you have all those the combined effect of these real form of the stresses, that means the sigma x, sigma y, tau xy, and you see because of those things there is a rotation, and that's why you see this theta angle is there. So if you want to calculate, you see either this one, the normal stress component at the oblique plane or the shear stress component at the oblique plane, is pretty easy, and these equations are well established. That means you see our Mohr circle is perfectly okay, and you see there is no ambiguity in that to say that the Mohr circle is the perfect graphical solution for analyzing the stresses, because you see the analytical equation is giving the same result, the graphical results are giving the same results, and that's why you see they are perfect matching. Thus the coordinates of Q are the normal and the shear stress of the plane inclined at the theta to BC in the original stress system. That means we can say that whatever you see, even after rotating by 2 theta, the coordinates of these things are nothing but equals to sigma x, and sigma y in the x direction if the normal stress is there, and the tau xy. This is the same. You see it's a combination of normal as well as the shear stress in a plane stress composition, and theta is always just making the angle with the BC of this particular plane. So this is, you see, from that now we can found some of the important observation, and these points are to be noted, that the direct stress is nothing but the maximum. Direct stress is the sigma theta is maximum when Q is at M, and this point obviously a shear. This point is the point where there is no shear stress is there. Meaning is that if you just go to the analytical solution, we found that if you differentiate the sigma theta by d sigma theta divided by d theta, and if you equate to 0, like we found that the sigma, like the plane is there, that is the 2 tan times of 2 theta p, like equals to sigma x minus sigma y divided by 2 xy. That is the, like the location where there is no shear stress, the principal stresses are there, and this was the analytical part. But if you compare that analytical part here to the graphical solution, we found that the direct stress is maximum. That means the theta, like sigma 1 and sigma 2 is there, and sigma theta is maximum when q is at m. Means you see, when the top q is matching to the m. If you go back to the figure, then you found that actually if the q and m is matching, then you see at this point there is no shear stress is there, because the vertical component is 0. Means there is no shear stress and the normal stress component is maximum. Hence, by definition, OM is the length, like representing the maximum principal stress is sigma 1, and 2 theta 1 gives you the angle of the plane, the 2 theta p, which we observed, where the theta 1 will be like always from the BC. Similarly, like OL is the another principal stresses and representing by sigma 2. Means that you see, like if Q is matching to M, we have a coincidence that actually, like whatever the stress formations are coming in the second most circle figure, it gives you the maximum value of normal stress, that is the sigma 1. It also gives you the minimum value of the principal stress, that is the sigma 2, and you see it always coming by graphically. So we can easily plot those, like the graph, this principal stresses on the principal plane by calculating this q2m and by calculating the 2 theta. So you see it gives you a graphical solution. No need to calculate those things. Just by like replacing those things, you can have all the solutions in your hand. So this is one for the maximum or minimum direct stress component. But you see the second point, if you go to the maximum shear stress, always it gives you given by the higher point of the circle, because you see on the vertical part, on like on the opposite you found that actually we have the shear stress component. So on the vertical axis, you are making a circle, the highest point of the circle which gives you the maximum shear stresses, or you can say that the like it is represented by the radius of circle. That means if you want to calculate, just you see if you remember the previous like the lecture, we discussed that if you want to calculate analytically that what is the location where the maximum shear stress is there, then it is tan 2 theta p is nothing but equals to 2 times of tau xy divided by sigma x minus sigma y. So this is the location. Now if you want to calculate the maximum value of these things, then it is nothing but equals to square root of sigma x minus sigma y whole square plus 4 times of tau square xy divided by 2. So this is nothing but the radius of the circle. So you see here by graphical solution also you can notate that the highest point of the circle which gives you the maximum shear stress, and you can also calculate from P origin to the highest point, and that is nothing but the radius of that, and you can also calculate from the circle as well as from the analytical solution. This follows that the shear stress and the complementary shear stress, that means the rotation and the anti-rotation rotational part of the shear stress, have the same value, obviously because we have the symmetric in the geometry as well as the applied conditions are pretty symmetric in the unit cube or parallelepiped. Therefore the center of the circle will always lie on the x-axis. Okay, so you see we have one axis which we are saying that like center is always lying, there is no eccentricity is there towards the axis midway between the sigma x or sigma y. Means that plus tau xy minus tau xy are the shear stresses, complementary shear stresses are there, and they have the same magnitude, only they have the difference in the sign. Means that you see always if you want to calculate the location of P, it is given by two way. One is the summation of sigma x plus sigma y by 2. So this is P. So you can simply like locate the center, or else if you are like notating these stress values, the normal stress value by sigma 1 and sigma 2, then easily you see we can put that what is the center position, or we can say the location of the center C is sigma 1 plus sigma y by 2. So you see here, irrespective of what is the symmetricity is there, it is simply lying on the axis, the x-axis, and it is always in between, or we can say the midway of sigma x and sigma y, or sigma 1 and sigma 2. And in that case also we found that there is a symmetricity, and that's why we always concerned about tau xy, never tau yx, or you see like because of the symmetricity this is always equal, tau xy equals to tau yx, tau xz equals to tau zx, or tau yz equals to tau zy. So this is due to the symmetricity. Okay, so here also we are considering those things. Only plus and minus signs are just the shear stress and the complementary shear stress. and they are counterbalanced to each other, and that's why you see we can say that the object is under well equilibrium because of these two components of the shear stresses. Now from the above point, the maximum shear stress, that is the radius of the Mohr circle, would be at like sigma x minus sigma y by 2. That means we can say that, you see, if you want to calculate the maximum shear stress, it is pretty simple, because like if you go back to that, then you found that this tau theta is nothing but equals to sigma x minus sigma y divided by 2 into sine of 2 theta minus tau xy cos of 2 theta. So now you see, if we put those things, if you want to get the maximum value, always you see the theta is at either 45, means theta is at 45-degree angle. That means you see now, like what we have the maximum value of the shear stress, that is the tau x minus sigma x minus sigma y by 2, because the tau xy will go on into the 0 part. So now come back to this point. You see, as we discussed, while the direct stresses are there, the P point, the center point, is always coming in between the sigma x and sigma y. So sigma x plus sigma y by 2 is nothing but this is the location, and this is my, you see, it is the radius. So if you want to calculate the maximum, this maximum value of the shear stress, it is always at the top, this top point of the circle, which is nothing but, you see, this radius from this P to this point, and this is nothing but equals to sigma x minus sigma y. So here you see, like if you want to calculate the direct stress, on the plane where the maximum shear stress is, the midpoint is there, you see, you can easily calculate by sigma x plus sigma y by 2. So this is pretty simple. You see, once you have all those, like the information, you can play with the graph, with this particular this diagram, and you can get those required values. So now you see, as already defined, the principal planes, which are the planes where there is no shear component is there, like the planes on which there is no shear stresses. That's why you see the shear, this principal stresses are there on this plane. Therefore, like we can conclude that the principal planes have no shear. Only normal stress components are there, means you see all those parallel forces are not at all concerning on these principal planes. Only you see, the perpendicular stresses are there on this particular planes. Since the resultant of these two stresses at 90 degree can be formed from the parallelogram, which you see we have shown in this of the vectors. So we can say that actually the parallelogram is a perfect diagram because it has unit width, unit this depth, as well as the unit thickness. So the parallelogram is a perfect thing because both, you see, the mutually perpendicular stresses can be easily shown then, and also we can say that the resultant of these two can also be at the 90 degree, which can be easily founded by those things. Thus the resultant stress on the plane at theta to BC is given by OQ on the Mohr circle. So you see here, whatever the O to Q was there, O to Q means O is that point and Q was that point. It simply gives you that actually what exactly the resultant for this resultant is there of these two stresses, which are like the mutually perpendicular to those things. So it's pretty simple, like to check all those points if you have the circular positions. So now go back to this particular things. You have, you see, the sigma, you have the tau, this is the resultant part, and if you know these values, it's pretty easy to get those other components of the stresses. The graphical method of the solution for a complete stress problem using Mohr circle is a very powerful technique, because it gives you all kinds of flexibility that you see, just rotate this angle and get those values, rotate this angle in the counterclockwise or the clockwise. You can get all those values by simply locating the points, rather than you need to do all the analytical analysis here. Since all the information relating to any plane within the stressed element is contained in the single construction. So once you that's what you see, I told you that it's lots of flexibility is containing that. That's what you see, we can say that it provides the convenient and the rapid means of the solution if we have the complex shear stresses, or if we have the complex normal stress component, or if we have the combination of all these stresses, which is less prone to this arithmetical errors, and is highly recommended. Only you see, now this is the beauty of this the analysis, that we have all kinds of flexibility to put the points that actually, okay, like if you want to calculate the sigma x or sigma y or tau xy, or if you have these values, you can easily go for the principal planes sigma 1 and sigma 2. You can also go for that where is the maximum value of the sigma 1 is there, the sigma x is there, where is the minimum value of the sigma x is there, where is the maximum value and minimum value of the tau xy is there, just by rotating the elements. So we can say that actually this method is highly recommended, where you see simply want to put those points and want to check those with the scaling only. But the problem is that actually if we have some higher values, then again what we need to do here, the basic drawback of this figure, this Mohs circle is that if you have some higher value of the stresses, or we can say that actually if we have some real values, means if let us say if you have sigma x is 50.20 and if you have the sigma y is 20.25, or if you have the tau xy is somewhere 15.45, then you see what we need to do here, we need to plot the graph, which is again you see and if you are calculating the those angles, then it contains some sort of the truncation error, means you see you are calculating, and when you are drawing when you are plotting those the 2 theta or theta, and then you see if you are calculating the what is the tan theta of that, or cos theta or sin theta, then it contains some types of error, and you see we cannot go beyond certain 2 to 3 digit, and then what we are doing here, we are summing up all the required digits of that, and that's why you see sometimes these assumptions gives you not exactly the answer, because analytical results always give you the perfect answer, but from graphical solution, as it is pretty standard thing is there, the graphical solution will not give you the exact solution. So in that case what we need to do, we need to restrict ourselves that actually if we have limited values of sigma x, sigma y and tau xy, or if we have the direct values like you see 50 Newton, this 50 kilonewton per millimeter square, or if we have the 20 kilonewton per millimeter square, or whatever like that, if this kind of the exact values are there of any sigma x, sigma y or tau xy, it's pretty easy for us to get the required values and to draw the Mohs circle. So this is you see the basic I should say the requirement of the Mohs circle. So in this lecture you see we found that the Mohs circle is also the the perfect solution for the stress calculation if we have you see the sigma x, sigma y or tau xy, or in the separate way or in the this combination way. So in this chapter you see we discussed about those things, and in the next you see lecture we just want to do some problems that actually if you have these values, then how to first draw the Mohs circle, and you see if we have the required values, whatever you see, how to calculate the desired value first, and second you see if we have the Mohs circle, then how to extract the information about the you see the shear stress or the normal stress component. So this kind of the discussion which we are going to discuss in the next class, you see that the numerical problems some 4 or 5 problems are there of the different the different values of the sigma x, sigma y and tau xy, as well as the different rotation, that actually if it is rotating by this angle, then in the clockwise or counterclockwise of the sigma x, sigma y or tau xy shear stress, if it is rotating like that, then what is the resultant is there, and what is the combined effect of those things are there. Thank you. Bye bye. Thank you.